today here, reaction types and enthalpy changes. Get your data booklets open, and we're going to open to page 4 or 5 here. And the first type of reaction we're going to look at is a formation reaction. And a formation reaction, make sure, listen closely, each element by itself, okay? And we'll give you an example of decomposition, what we're talking about here, but formation is each element by itself reacts to form some type of compound, okay? The formation, heats of formation is what that's called, is found in the data booklet. So when you open up to page 4 and 5, okay, here is, like I said, all the compounds that we don't know, they're in here, and plus some we do. And the heats of formation, how much energy is required, what happens when you form these compounds. Okay, you'll see some are negative, and some are positive, of course. Okay, and in fact, you'll see that, well, anyway, there's some negatives, there's some positives. Okay, so those are the heats of formation. That's what this booklet tells you. And also it'll tell you in the top right corner here, delta FH, okay, the little dot there, the little circle just is a notation thing, don't really worry about that too much, in kilojoules per mole of that, okay, just like we did kind of on the last sheet there. So let's not forget that as well. So let's take a look at our first example here. If we want to write the formation of dinitrogen tetroxide, we'd say, well, first of all, we should probably know what dinitrogen tetroxide looks like, yes, from Chem 20. Molecular compound, obviously, prefixes, yeah. Dinitrogen tetroxide would look something like this, N2O4. If you're not sure, you look it up in your data booklet here. It tells you that it's actually a gas, okay, so it actually tells you that state in here. So this will be a gas here. Okay, and if I want to make that, I need, of course, each element by itself. Nitrogen is a molecular element. I have no brighter, clever friends, people stupid. I gave you those the last day, yes? Don't forget for this as well. So nitrogen, and I need some oxygen, of course. Okay, you need to balance it. So pretty straightforward balancing, I think. 2 there. Okay, and that's what we would have done in Chem 20, yes? Okay, balanced formation of dinitrogen tetroxide. Now in Chem 30, we're going to associate the enthalpy change, or basically the heat or the energy associated with this question. So we're going to look up N2O4. N2O4, where are we here? Once again, dinitrogen tetroxide, alphabetical order. So look under D. Okay, find D there. It's the first one for the D's. It's the only one for the D's, actually. And it's a positive 11.1 kilojoules per mole. Okay. So the number that's associated with this is kilojoules per mole. Okay? Well, how many moles of dinitrogen tetroxide am I forming in this balanced chemical equation? 1, right? So I need 11.1 kilojoules for every mole that I want to make, right? I'm only making 1, so I need 11.1 kilojoules. If I'm going to, let's say I'm going to do this as a term within the equation. A term within the equation. Left side or right side? What do you think? Who says left? Who says right? Who doesn't know anything? All right, well, we're going to put in left, okay? It's endothermic. It's positive, right? It's going to absorb that energy. It has to be put onto the left side. Endothermic, of course. Remember, think back to yesterday's work. Where do we put endothermic ones? Where do we put the ones that absorb energy? We put them on the left side, right? Because you got to put that energy in to make this compound in this particular case. So, balanced chemical equation, a term within the equation would look something like this here, would be my final answer. Okay? A term within the equation, right? And we could go through all 3 things again, and that's what actually the homework might ask you to do, a few different ones. Yep. You would have put it on the right-hand side. Okay, so, and if you wanted to, okay, that's a term within the equation. Just for a little review here real quick, we could say, oops. If we're going to write delta H notation, we put a positive 11.1 kilojoules, like so. Okay? So that would be delta H notation. We could also do a potential energy diagram, endothermic one. Yeah. Well, that's just a different way of writing it, right? So you have to know the 3 different ways. Term within the equation, right? Delta H notation, which is just a delta H after the equation, and then of course potential energy diagram would be the other one. No, not really. No. But they're going to ask you, they're going to ask you on the diploma one of the 3 types basically, and they're going to be specific about which one they want. Okay? So that's formation of dinitrogen tetra. Good so far? Yes? Questions? Anyone? Questions? Okay? So, decomposition, simple decomposition. Okay? The reactant, of course, is the compound which is broken down. So we're going to flip this around. We did formation. We took each element by itself and we made a compound. Now we're going to take the compound and break it down into each element by itself. Simple decomp. Sometimes you will see delta SD or simply delta DEC, or delta D also might be an option down here. Right? We talked about that last day. SD just stands for simple decomposition. D would stand for decomposition. Okay, so either one, whatever, doesn't matter, but it's decomp. Okay. Now, in the data booklet, this is the important part. Listen carefully. Okay. Especially for some of you guys. This is formation stuff. This only is the formation numbers. If you want to do decomposition, it is the opposite of this number here. So for the last one, we had a positive 11.1. If we wanted to do the decomposition of that one, it would be a negative 11.1. Okay? So decomposition is the opposite of formation, right? And that's what it tells you right here. The negative of the delta F, delta formation. So make sure you make note of that however you want to. If that's good for you, that's fine. Make little notes for yourselves. Decomposition is the opposite of what you see in here. Okay? All right? So let's take a look here. If we're doing the decomposition of magnesium carbonate, well, first of all, magnesium carbonate, we should hopefully know, looks like this here. Magnesium carbonate is a magnesium 2 plus, carbonate's a 2 minus. This is on a compound, of course, a metal and a polyatomic ion. 2 plus, 2 minus, swap, drop, and reduce. Yes? All ionic compounds, unless you put them into water, are solids because they're very good at sticking together. That's called ionic bonding. Okay? So that's solid. If you don't know that, look it up in here. It tells you. Okay? They're not all in here, so yes, you still need to know ionic compounds. Magnesium carbonate does happen to be in here because I want you to use that number, so that's why it's in there. When you break this down, it's each element by itself. Like so. Okay? That is simple decomposition. Each element by itself. When you heat up magnesium carbonate, you most certainly don't get magnesium 2 plus and carbonate 2 minus. No, that's what happens when you put it into water. That's dissociation is the term that goes with that. We will maybe do a little bit of that, but that's not what we're doing here. This is decomposition, each element by itself. Balancing this, let's see here. Well, oxygen is going to be the problem. We got 3 there and 2 there, so let's do a double here and 3 there to get 6 on both sides. And then we'll go 2 here and 2 here. Okay? Now, you're going to look up magnesium carbonate in the booklet here. Magnesium carbonate, that's actually second last one on the first page here. Magnesium carbonate is a negative 1095.8 kilojoules. Okay? That's for formation. So for decomposition, it's a positive. Okay? So delta H here for decomposition would be a positive 1095.8 kilojoules per mole. It's the opposite. Yes? So, once again, for formation, it is negative 1095.8. For decomposition, it'd be a positive 1095.8. Yes? Okay? I know some of you guys are like, duh, I get this. But I just want to make sure because this is kind of important. These are little things that'll really do you over here. So we got to flip the sign because we're doing decomp. And it's per mole. Well, how many moles are we decomposing here, guys? We're not decomposing 1. We balanced it. It says 2. So we need to have twice as much, right? This is what we did on Friday as well. You had a question like this. So, first of all, where are we going to put this? Left side or right side? Right side or left side? How many people say right? This is where I wish I had a little tool here. Right side or left side? Left, I hear left, left. It's endothermic. Look, it's positive 1095. Okay, so we need to put it on the left side. So 2 magnesium carbonates. And not 1095 though, because remember that's per mole. We're doing 2 moles here, so twice as much, right? So what is that? Somebody help me out here. 21, what, sorry? Thank you. Kilojoules, okay? 2,191.6 kilojoules will give me 2 magnesiums, 2 carbons, and 3 oxygens. Okay? Good? Questions, anyone? Okay? Now this isn't, we haven't got to the tough stuff yet, but these are little things that can make a big difference, obviously. Okay? So we have to be careful of these, all right? And that's why we're spending some time going over these equations here. All right? So first of all, this is decomposition. It's the opposite number in the data booklet. That's for formation. We want decomp. It was negative 1095 for formation. We're going to change it to a positive 1095 for decomp. That's per mole. We're breaking down 2 moles according to the balanced chemical equation, so I need twice the amount of energy or heat. Okay? Good? Yes? I need to talk to you guys over here more. All right. Combustion reactions. Most of the time when we talk about combustion reactions in Chem 30, we talk about a hydrocarbon. Hydrogens and carbons mixed together. Okay? Most of the time the 2 products you're going to get, carbon dioxide and water. Okay? Each fuel has a unique molar enthalpy of combustion, delta CH. You're not going to find this in the data booklet anymore. This is only formation, and of course we adapted it for decomp. This doesn't do delta CH combustion or any other reactions for that matter. Can you use this to help you find that? Eventually, yes. You're not there yet. Okay? So I need to tell you the delta CH for this equation based on each fuel. If you burned a mole of octane, which we had the other day, that's a different energy than if you burned a mole of propane for in your barbecue, for example, or a mole of butane from a lighter. Okay? All those have different energies associated with them. You can't find them here. These are formation. This is to make propane or butane or octane. That's what these numbers are. To burn it, it's different. I'll show you how to figure that out later. Stick around, okay? Hopefully. So, the combustion of ethane, they're going to tell you delta CH, okay? And they're going to be specific. It's for ethane, of course. Ethane is, let's see here, C2H6, I believe, yeah? Yeah. C2H6, and it's liquid? Gas. Okay. Yeah, I thought it would be a gas, but for some reason I have liquid in my head here. CO2 and H2O. Oh, combustion, by the way. Sorry. So, C here, right? C in the fuel, you get CO2 gas. H here, you get H2O gas. Yes? Okay, combustion. Chem 30, that's what we focus on most, those 2. Okay, we don't really care about the sulfurs and the nitrogens and the other stuff, the metals, although it could happen, but not likely. Balancing wise, let's see, 2 carbons, 2 carbons. 6 hydrogens, I'll put a 3 there. That's 4 and 3 is 7 oxygens on that side. On this side, how am I going to get 7? Well, like I said, I don't know, if you had me last year, this is what I did. I said, well, that's 7, how would I balance it on this side? I'd put 3.5 here. And then I'd say, well, can I leave it like that? And the answer is, well, not really. It's not the best. Is it balanced? Yes. Do I have 7 on both sides? Sure. What would I do? Probably go back and double everything. That probably makes the most sense. So I'm going to double C2H6 gas, double this, so 7 oxygens, gives me 4 carbon dioxides, and 6 waters. And Is that balanced? Yeah, it is, because I know the first one was balanced and I just doubled it. Why do I double it? Because I get rid of 3.5, right? Becomes 7 now, a whole number, okay? So you can double check it if you want. 4 carbons, 4 carbons. I got 12 hydrogens, 12 hydrogens. I got 8 and 6 is 14, and I got 14 there, okay? So it's all balanced. And if you don't want to do the first step, then don't. I don't care. Figure it out, okay? You're in Chem 30 now, so you'll be fine. All right? Now, this here, it tells you the delta CH for ethane is a negative 1516 kilojoules per mole. They're telling you that for ethane. That's particularly for that right there. So when I burn 1 mole of ethane, I get 1560 kilojoules of energy produced per mole, right? That's for 1 mole. I'm burning 2 in this balanced chemical equation, right? 2. So if I want to burn 2, I'm going to get twice as much, right? Yes? It's a negative 1560, so where do I need to put it? Left side or right side? Right side. It's a product. It's exothermic. That's what the negative tells you. It's exothermic, which means I'm getting energy out of this system. Think about it. You're burning something. When you burn something, it makes hot. Yeah? You're getting energy out of it. That's the purpose of burning it. When you're sitting by the campfire, you're burning wood to make it hot. That's what makes it enjoyable when you're drinking Pepsi, right? So we're going to put that on this side, the right side, 1560. But remember, that's for 1. We're burning 2. So we got to double it. So what's that? 3120? Is that right? Okay, 3120 kilojoules. It's not kilojoules per mole anymore because remember, it's kilojoules because that's how much energy I'm going to get out of this system, right? For 2 moles, it's not per mole anymore. This is for 2, so I'm going to get twice the amount of energy, kilojoules, right? This is how much you get for every mole that you burn. I'm burning 2, so twice as much, 3120, okay? You could do delta H notation as well, sure. Same thing here, basically, balanced chemical equation, CO2, gas, 6 waters, right? And then over here you'd say delta H is a negative 3120 kilojoules. Okay? You could do a potential energy diagram, same thing as last day. Yeah? Good? Yes, no? Questions? All right? Good? We're going to do single replacement reactions. So remember, the metals switch places. All right? Usually you start with a metal and you're going to switch it with a positive ion. Same thing in this case. You're not going to find single replacement reactions in here, okay, for right now anyway. This is formation and decomp. That's all that's really good for the time being, okay? You want to do single replacement reactions or double or combustion, they're going to tell you specifically a number for that, okay? So aluminum reacts with hydrochloric acid. Aluminum and hydrochloric acid. So who remembers what hydrochloric acid is? Huh? Hydrochloric acid. HCl? Well, look it up in your data booklet. There's a list of them there for you now. Yeah, it's HCl. So last year when I made you memorize how to write out the formulas for hydrochloric acid, and people are swearing at me right now in their head, hey, because you're appropriate in this Catholic school and we don't swear. We shouldn't, hey? Now you're thinking, geez, why didn't I have this list last year? Well, because that's part of the Chem 20. You need to be able to write acid formulas. That's part of the curriculum, okay? Now, I guess they assume that you forgot how to do that from Chem 20, I guess. I don't know. But now they give you a list. I'll tell you where the list is. Pretty much every acid we're going to use is going to be on this list on page 8 and 9. There's a big list right there for you. So if you forget, okay, I'm not going to lie to you. If you're going to look at this for every acid, well, it's going to take you a while, okay? And when you're doing 60 questions in 2.5 hours, you know, it's going to slow you down a little bit, okay? If you don't know what hydrochloric acid is or sulfuric or some of the bigger ones, okay? Or for that matter, at least the top 6 you should know, okay? And we'll talk about that in Unit 3 stuff, or 4, sorry. Hydrochloric acid, strong, that's one of the 6 at the top, okay? And it is HCl. If you forget they're in there somewhere, you're going to have to look for them. Okay? So hydrochloric acid. Acids have to be placed into water, of course. So AQ. And we're going to do a single replacement. So aluminum and hydrogen are going to switch places. Hydrogen is going to come out by itself, which of course is a molecular element. So it's a gas, H2. And aluminum chloride would be your other product here. Aluminum's a 3+, chloride's a 1-, so we need to swap drop. Yes? And this, of course, is aqueous as well. Okay, the other part of the solution. Balancing wise, well, you know, I don't know how quickly you want me to do this here, but there's 2 hydrogens here. I could put a 2 here, but then I have 2 chlorines, and that's 3 chlorines, so that's going to be the problem. So we're going to put a 6 here, and I'm going to put a 3 here, and a 2 there, and then a 2 there. Okay? And if that was too quick for you, well, you have to remember I've done 1 or 2 of these a few times, so you'll figure it out eventually. Okay? So, balanced. Okay? Now, the delta RH, the reaction, by the way, that's what that stands for. So the reaction enthalpy that's involved with this is for aluminum, that one right there. So that's all I care about in this particular reaction. Is there one associated with hydrochloric acid? Sure there is. Okay, what is it? I don't know. Okay, don't care either right now, because I specifically want you to use the aluminum here. Okay, it's a negative 256 kilojoules per mole. So first of all, should I be putting this number on the left side or the right side? Left side or right side? Huh? Right. The right side. It's negative, it's exothermic, it's giving off energy, right? So I should be putting it on the right side. Secondly, so I'm going to write it on as a product here. And secondly, of course, this is 256 per mole. I'm using 2 moles here in my balanced chemical equation. So of course, instead of 256 there, I'm going to write, I know this, don't tell me, 518. No, 512. 512. So plus 512 kilojoules of energy, probably in the form of some kind of heat, I imagine, is going to be a product here, 512 kilojoules. Good? If I was writing delta H notation, I'd say negative 512 kilojoules, right? And if I was doing a potential energy diagram, I'd start up high, I'd drop down, and I'd write the balanced reactants, balanced products, and say delta H is a negative 512, yeah? Okay, all those things. Good? Questions? The negative tells you where to put it, right? Negative, exothermic, going to give off heat, products. If it's a positive, left side, I have to put that energy in for this reaction to take place. Okay? And finally, double replacement. 2 ionic compounds, or usually acid and base, are good ones for these ones as well. With an acid base, you might see delta H neutralization, N-E-U-T. I think I wrote that one down the other day. Right? So you might see that sometimes, which basically means neutralizing. Okay? Or double replacement or whatever. Okay? Or, like I said, for this reaction, it's still a reaction, you may see delta RH. Okay? One of those 2. Once again, it's just a notation thing, and it'll tell you specifically for what reactant or whatever the case might be, what the enthalpy change is associated with that. Okay? So, 2 ionic compounds. Let's see here. Calcium nitrate. Calcium's a 2+, nitrate's a 1-, of course, so we need to swap and droppy. That will be aqueous. Remember, double replacement, we want 2 solutions mixed together. Aqueous. Yes, is that ionic compound? Yes, it is. But if you mix 2 solids together, what's going to happen? Probably not a lot. So we want to have 2 solutions reacting together. Calcium nitrate reacts with ammonium phosphate, ammonium, an H4 positive, phosphate's a 3-. So we need to make sure we get the right formulas here, otherwise the balancing's never going to go well for us. Ammonium 1+, phosphate 3-, swap and drop, that's also aqueous. And that's going to give me, I'm just going to give up now. I'm not going to fit that in there, so I'm just going to do that. going to give me double replacement reaction. So positive parts switch places. Calcium's a 2+. That's going to switch with ammonium, which is a 1+. So ammonium is going to come with the nitrate. And calcium is going to go with the phosphate. And of course, calcium is a 2+, and phosphate is a 3-. So we need to swap and drop there, right? Like so. We really should put states with this, right? Technically, I mean, that's something we should be able to do. Okay, I expect you to be able to do that in Chem 20 as well. So to look up states for those, in other words, which ones are aqueous, which ones are solids, which one's the precipitate here, because in double replacement reactions we quite often get precipitates. You'd look at your solubility chart, which is also in here. And you'll know they're all the same, guys, because that's where I took all this stuff for Chem 20, right? So you're going to find ammonium nitrate, find nitrate across the top, NO3-. It's in the very first column there. Most of the stuff, which is where the ammonium falls into place, is that's soluble. So that's going to be aqueous here. And, you know, that one's a little bit tricky to find, but look at phosphate. Find phosphate across the top here. There's phosphate right there in the middle kind of thing. Where's Ca2+? Is it one of the ones listed in the first one there? No, it's in the most category, so that's your solid there. So that would be your precipitate, actually. Okay? And you would see that, of course, if you went to the lab and mixed these two ionic compounds together. Okay? Balancing-wise, yep. Hey, sorry? A gas? Which one? I don't. Usually only in single information reactions. So it's either got to be on page 4 or 5 for you to know it's a gas, one of those compounds, or it's got to be simple formation or decomp, and it'll be the ones, well, in your data booklet it's a little different colors. I forget what the color is in your data booklet for gases, but if you look up there, it's the ones in the red writing, right? And on your data booklet, you can kind of figure that out here. I'm not sure which one it is here exactly. I guess it's the blue ones are your gas. You can look them up in your periodic table here. So first page there, periodic table. All the charges on there, right? So whichever ones you can find. The metals are on there, and I guess we probably will mention one other thing about that too. Okay. All right. Balancing wise, let's see here. Well, I got 1 calcium here. I got 1 calcium or 3 calciums there. Let me start by putting a 3 here. Now you might always have to go back and fix these. I mean, it's kind of trial and error, right? So 3 calciums, 3 calciums. I got 6 nitrates, right? 3 and 2 is 6 nitrates. Let me put a 6 here, 6 nitrates. I have 3 ammoniums. Here I got 6 NH4s. So I'm going to put a 2 there. So 6 ammoniums, 2 phosphates, and we should be done. Okay? Yes. So that's the balanced chemical equation there. Now, once again, we need to associate the enthalpy change here. This here, they're telling you for this reaction, calcium nitrate, for that particular one, okay, and I don't care about the ammonium phosphate in this case, and I'll actually mention something about that in a sec here. It's a negative 36 kilojoules per mole. Left side or right side, if I want to include this as a term within the equation, right side. So we're going to put in a positive right here, 36 kilojoules per mole, but here, look, I'm reacting 3 moles. For every mole, I get 36. If I'm reacting 3 times as much, of course, 100 and what, 8? Yeah, 108 kilojoules is a product from this particular reaction. Okay? Good? Questions? And then, of course, you could do delta H notation, etc., etc. Questions, anyone? Questions? Ask. It's okay. Ask. Okay? Couple things. First of all, is there a delta? Is there some kind of energy associated with that? And the answer is yes, there is. But do I know what it is? I don't know what it is right now because I didn't give it to you. I'd have to look it up probably, et cetera, et cetera. I don't care. Okay. If you're doing this reaction, okay, if you think back to Chem 20, more than likely what's happening here is this is a limiting reactant here. If you remember that term from Unit 4, right, Stoic? Remember we talked about, hey, this would determine, for example, you know, in this question here, what would I ask you from Unit 4, Chem 20? I'd say this calcium nitrate determines how much precipitate I'd get, right? Remember that? And you'd figure out N, et cetera, and so on, right? And you'd figure out the mass and all that other stuff. Well, that determines that, okay? In Chem 30, I would say, well, this determines that, right? Because this is kind of like my limiting reactant. I have 3 moles of that, and as a result of that 3 moles of that, I'd get 108 kilojoules produced, okay? So that's what we're going to do in Chem 30, really. That's all it is, towards the end. Stoichiometry with that, okay? That's how it changes, all right? We've got a little ways to go before we get to that part, though, okay? So that's basically the 5 reaction types. Questions? If it's a positive, remember it's endothermic, we want to put on the left side. If it's negative, right side, exothermic, okay? Calculating amounts real quick, there's 2 quick examples for you. Don't forget there's a few ways, because we're going to use these, of course, so I just threw this in to kind of, we didn't have this lesson for a while here, and then we threw this in here just to kind of review the 5 reaction types, and of course, how do you find amount, right? Well, you could use the mass, which of course is in grams. This is in grams per mole, and this, of course, would be the amount here, right? Whenever you see the word amount, we're looking for N. Yes, you know that from last year, moles, okay? And of course, the other formula I would have given you guys last year was C equals N over V, or whenever it was for you guys, I don't know. C equals N over V. And if we rearrange that, C equals N over V, we get N equals C times V. And of course, C is the molar concentration. Okay? V is in liters. And of course, if we multiply those two, we get the amount in moles. All right? So, good. Real couple quick questions here, just for a little review. Okay. We got all those copied down? Yeah. All right. So, for example, what amount of potassium phosphate has a mass of 225 grams? What amount? A mass of 225 grams. Grams would go here. Molar mass would go down there. Potassium phosphate. K is a 1 plus. Phosphate, of course, is a 3 minus. Okay, so swap and drop. So we'd get, as a result, of course, K3PO4. Okay. K3PO4. Unfortunately, I kind of forget what that was from last class here, but 39.1 times 3, what is it, 30.97, and 212.27. 212.27 grams per mole. And in this case here, we take, final answer would probably be about 1.06 moles. Okay, 1.06 moles. So that's how you could find the amount. Yep. It's up here, PO4. Okay. So about 1.06 moles. All said and done, rounded significant digits. We got 3 in the question here, 225, so that's 3. So probably 3 in the answer. Okay. And once again, in most cases, it'll tell you on the diploma or in the particular question how many digits you want to have. Okay. Next one here. We got some sodium hydroxide, 220 milliliters. and it's got a 1.30 times 10 to the negative 2 big M. When we talk about concentrations, okay, and I definitely used this term last year if you're in my class. We talk about concentrations, and you see, like, sometimes it's italicized, sometimes it's not. It really depends. When we talk about concentrations, that means moles per liter, big M. Okay, so we call it molar. So 1.30 times 10 to the negative 2 molar solution, which basically refers to moles per liter, of course. If we're going to do this one here, we would do C over V here, N equals C times V. So if we want to find the amount, we would take, of course, C here, 1.30 times 10 to the negative 2 moles per liter, molar, okay, and multiply it by the volume, in liters, of course, and the volume is 220 milliliters, or 0.220 liters. All right. Multiplying those two together will give you, well, your answer, of course. Let's see, 1.3 times 10 to the negative 2 times 0.22. It's 0.00286 moles. And if this is going to be probably in some kind of, there's nothing wrong with that answer, but if you need to put in scientific notation for some reason, of course, which is probably what you'd have to do, it'd be 2.86 times 10 to the 123 moles, negative 3 moles. Okay? Like so. Good? Once again, probably, excuse me, 3 significant digits, because that's what's in the question, right? 3, 3,